Have you ever looked at a number and wondered, could this number build itself? Normally, when we see 25, we simply read it as 25. But mathematics gives us another way to look at it. A number doesn't always have to be just a final answer. Sometimes it can also be a construction. So, here is the question. Can a number use its own digits to recreate itself? Let's start with a simple example 25. Its digits are 2 and 5. Instead of treating them as one number, let's use those digits as mathematical building blocks. Take 5 as the base and 2 as the exponent. We get 5 square equal to 25. Look at what happened. We started with 25 and used its own digits to rebuild 25. That's the basic idea behind a selfie number. Now, let's try something a little more interesting. Take 145. Its digits are 1, 4 and 5. This time, we can use factorials. 1 plus 4 factorial plus 5 factorial. Remember, factorial means multiplying all the positive integers up to that number. So, 4 factorial equal to 24 and 5 factorial equal to 120. Therefore, 1 plus 24 plus 120 equal to 145. Once again, the number has recreated itself using its own digits. So, already we are seeing something important. Digits don't always have just one role. We can use them as building blocks in different mathematical ways. Now, let's look at selfie numbers in a different way. Imagine that every digit is a Lego block. The digits are our building pieces and the mathematical operations are the connectors. Addition can connect pieces. Multiplication can connect them in another way. Powers can create another kind of structure. Parentheses can tell us which pieces should be grouped together. So, instead of thinking I am just calculating a number, we can start thinking I am building a mathematical structure. And this Lego idea becomes especially useful when we move from selfie numbers to selfie fractions. And now we can ask a bigger question. What happens if we take this same idea and apply it to fractions? Now we don't have just one number to construct. We have a numerator and a denominator. Their digits can also become building blocks. We can keep the digits in the same order, decide where to split them and insert mathematical operations. And that's where we enter the world of selfie fractions. Depending on the operations we use, selfie fractions can take different forms. In an addable selfie fraction, addition becomes part of the construction. Let's say we have the digit sequence 18, 26, 734. We can connect these groups using addition. This is an addable construction. The interesting part isn't just calculating the result. The real puzzle is where should we split the digits so that the mathematical relationship works. Now let's change our connector. Instead of addition, let's use subtraction. For instance, 20, 435, 7 becomes 20 minus 435 minus 7. Notice something important. We didn't rearrange the digits. We only changed the way the blocks were connected. In an addable selfie fraction, addition becomes part of the construction. In a subtractable selfie fraction, subtraction takes its place. The interesting part isn't just performing the operation. The real challenge is finding a split that actually works. It's almost like trying different Lego connections until the pieces form the structure you want. But addition and subtraction aren't only our choices. We can also use multiplication. These are called Dottable selfie fractions. Powers can also be part of the construction, giving us potentiable forms. Sometimes different operations can be combined. addition, subtraction, multiplication, powers, parentheses. Now our Lego box has many different connectors. Now let's try multiplication. For example, 1, 36, 24 becomes 1 times 36 times 24. Same pieces, same order, different mathematical construction. Now let's make the puzzle harder. What if multiplication joins the construction? Or what if we combine addition and multiplication? Suddenly we have several choices. Should these two digits stay together? Should I split them? Should I add? Should I multiply? Should I use parentheses? At this point, we are doing something very similar to a search problem. We are exploring possibilities and checking which ones work. But what if we don't stop after finding just one valid construction? What if we notice that the construction follows a pattern and we can keep extending it? That's where pattern selfie fractions come in. Instead of finding just one interesting fraction, we can discover a whole family of related fractions. It's like building a Lego train. You can create the first carriage, then you add another, then another. The train gets longer, but the basic design stays the same. But finding one valid construction isn't the end of the puzzle. What if the same fraction can be constructed in more than one way? Think about a Lego model. You may have one finished structure, but discover another way to connect the same pieces and create an equivalent structure. That's the idea behind equivalent selfie fractions. Another family is the digit split pattern. Here, we divide the digits into particular sections. Then one section grows while the same structure rule continues. For example, imagine 32 becoming 332, then 3332, then 33332. What's happening? We repeatedly inserting another 3 into the same position. The number gets longer, but the structure remains recognizable, just like adding another Lego block to the same part of a model. Now, let's bring another beautiful mathematical idea into the picture. Symmetry. A palindrome has a special property. It reads the same from left to right and right to left. For instance, 121 or 1331. In palindromic selfie fractions, this visual symmetry becomes part of the mathematical structure. So, now we are asking two questions. Does the mathematics work? And does the number have a symmetric structure? Mathematics suddenly has another dimension, not just value, but visual structure. Now, let's step back for a moment. We have seen selfie numbers, selfie fractions, equivalent representations, multiplicative patterns, digit split patterns, palindromic patterns, same digit patterns. They may look completely different, but underneath all of them is the same habit of thinking. Find the structure, understand the rule, test it, and then ask, can this pattern continue? And this is where selfie numbers connect beautifully with computer science. Imagine giving one of these puzzles to a computer. We could ask, can you find another valid representation using these digits? The computer could try one split, then another, try addition, try subtraction, try multiplication, check the result. If it doesn't work, try another possibility. This is similar to algorithmic search. We break a problem into smaller choices. We explore possible solutions. We test them. We reject the ones that don't work. And when we discover a pattern that keeps working, we can turn that pattern into a rule or algorithm. So, what started with a simple question, can a number rebuild itself, has taken us much further. We discovered that digits can become building blocks. We saw how mathematical operations can connect those blocks. we moved from selfie numbers to selfie fractions. We discovered that the same fraction can have multiple representations. Then we found patterns that can grow into entire families. And finally, we connected that way of thinking to computer science because the real lesson isn't just about unusual numbers, it's about problem solving. So the next time you see a number, don't just ask, "What number is this?" Try asking, "What can I build with these digits? Can I find another representation? Can I discover a pattern? Can I extend that pattern? Can I turn the pattern into a rule?" Because sometimes mathematics isn't just about finding the answer. Sometimes the real challenge is discovering everything the numbers can do.